Well, let's get going. It's 4:30, and we're doing special topics today. Zoom was on strike, and now it's back up. So maybe some of you will join us a little bit late that way too. So we're looking at some topics that combine linear algebra and calculus. So we're going to start with Fourier series. You can download this handout from Canvas. So it's in the lecture folder. Max can post it here in case that's hard for you. So I'll give you just a minute or two to get that set up. Let me know when you're ready. Okay, we're ready. So Fourier series are a method of reducing any piecewise continuous periodic function to a series, to a countable set of numbers. Those numbers are the coefficients in the Fourier series. So here's a classical Fourier series where you write the function as a constant and then an infinite sum of coefficients times cosines, and we have harmonics here. So these are called a harmonic series. When k equals 1, you just got a function that has period capital T. When k is 2, it has period t over 2. When k is 3, it has period t over 4, etc. So all of these different multiples of the fundamental frequency, which is 2 pi over capital T, are called harmonics. And you're probably used to that term from music. And we'll see there's a straightforward integral one does to calculate the coefficients in the Fourier series. So what I want to first do is just go through an example. So here's sine of t and all of its in its first 10 harmonics. So you can see the fundamental, and then with k equals 2, 3, and 4, etc. Cosine looks exactly the same. We'll come back to the real exponential. So what I want to do first is just to help you build up your intuition. Here's some standard periodic signals.
Oh, Crystal Kane's thing, I realized that you can't see the screen. You can only see it from behind you.
Oh, all right. Okay, let me fix that. There we go. Okay, so we'll go back. So here's some standard periodic signals. We're going to calculate their Fourier series. So notice that here's the period, and this is just a sinusoid, and whether it's sine or cosine doesn't matter. You just shift by pi over 2. Here's a square wave. Notes that it's periodic, it has the same period as the sine. And then it repeats. So 2 blocks here is 1 period. Here's a triangle wave, and exactly the same. It goes up, down, and then it just repeats. This is called a sawtooth wave. goes up, and then it jumps down, just like the square wave. So this is not a function the way we've drawn it, but we know that visually we just put the lines in to help us see the square wave, and it's the same thing here on what's called the sawtooth wave. So it looks like the blade of a handsaw if you were trying to cut a piece of wood. And it goes up and down, and then it repeats, up, down, back, up, down, back. So there's 3 periods of each of these signals here. So to get some intuition, okay, so here's the very first term in a Fourier series for a signal. Can you figure it out from that? Obviously not. Okay. But what if I give you 2 terms of it? Got an idea? Who wants, you have a guess? Anybody online want to guess first, and then we'll let the room guess? There's 2 terms. There's 3 terms. So what we've done is taken the signal, and this is adding up the first 3 harmonics. So whatever the period is, it's got sine of that, it's got sine of that period over 2 and that period over 3 added up. No clue? You got a clue what that one might be? Yeah, you're right. It's a triangle wave. Good guess. Good guess. So that's the triangle wave.
Oh, just the shape. I thought you were asking about coefficients.
No, we're asking about the waves. So name that signal. So if you've ever seen the game, Name That Tune, where they'll say, I'll name that tune in 3 notes or 7 notes. We're playing a similar game here. How many terms in the Fourier series do you need in order to recognize the wave? And this one has, in this picture, there's 75 terms in the Fourier series, and it looks perfect, okay? Yep, and there's 100. Okay, let's get a new signal. Any idea what this one is? 1 term? They all look the same, okay?
I guess they square.
Now you've got 3 terms, terms 1 and 3. 1, 2, 3, they're all added up, okay? Can you start to see that it's sloping up and maybe it's trying to drop down quickly? Got a guess now online, folks? You want to tell me what you think this is? I'll remind you of your choices here. It could be a sinusoid. Ah, sawtooth. That's looking pretty good. Okay. And we'll do a few more. Hey, what happened to my enter? No, don't do that. Okay. I moved my mouse out of the, so I'm gonna have to restart. In lab. In the lab, yes. And we'll restart the lab. So you can download the handout from Canvas. We're playing a game, Name That Signal. It's just like name that tune, okay? I'm going to give you different pieces of the Fourier series, and you got to tell me what it is. Hey, come on. I ended the lab. Come on. Okay. Got my kernel. Okay, now we got it going again. Kernel still connecting.
Sleepy today.
What did I do wrong?
Kernel's a little sleepy today. Maybe bought hard. Yeah, looks like I'm getting there.
Yeah. It's happened enough times that I don't freak out anymore. I just sit here patiently and punch buttons. Well, maybe not so patiently. Come on, it's not that hard. Kernel's good now. Now we're running the cell. On your mark, get set, go. Did you guys find the handout? Did you find my kernels? I can't. Let me know when you find my kernel. Come on. This is a really easy function to run.
After another second, maybe on your bottom right, interrupt the kernel. Don't end the lab, but yeah.
You want me to restart it?
Or interrupt it and then restart. See if it works.
Okay. Should run like that. There we go. Good. Okay, so the idea, so online, folks, we're restarting, unfortunately. So you can't tell, so this is a sum of sinusoids, this signal. And here are your choices. Sinusoids, that's sine, cosine, square wave, triangle wave, and sawtooth. And I'm gonna, can you tell what this one is going to be? Got a guess? What's it looking like now? The sawtooth has a discontinuity, just like the square wave has a discontinuity. A sawtooth has a discontinuity, then it goes up and comes back down. So that's the triangle wave. Now we get a new signal. You've got the first term in the Fourier series. Can you tell what it is? Not so much, right? That's not enough information. Okay. There's 3 terms. 7. Now you got it. Yeah. Everybody got it. Sawtooth. Yeah. Let's just do a few more. Now, because it's discontinuous, it takes many more terms in the Fourier series to get the good approximation. So this is what Fourier's colleagues couldn't wrap their heads around, is that how is it possible to add up continuous functions? Sinusoids are continuous. And if you do a finite sum of continuous functions, it's continuous. So how is it possible to write a discontinuous function, a function with jumps, as a sum of continuous signals? And the key thing is you need to use a lot of sinusoids. And in the limit, you get it perfectly. With 100, it's still not quite perfect. Okay, here's another signal. Obviously, we have no clue. You may have a guess now. You're going to name that signal in 3 terms?
Square.
Okay, you just lost your house. No, you won. You won the grand prize. You get extra, you get double snacks today. Yay! Okay, now it's discontinuous as well. And notice how it's having a hard time getting that flat and to jump up and then go flat. I mean, sinusoids want to wiggle. And that's called the Gibbs phenomenon, if you want to look into it more heavily. Okay, so this is a mystery signal. This is the first 3 terms of the mystery signal. No guess? Okay, online, you got to beat the folks in-house. Okay, there's 7 terms on the right. Oh, come on. Any better? Confusing, huh? How about that? You got a couple of periods. Let me just say that everyone watching this lecture, everyone watching the lecture has one of these signals. Okay? You possess one of these signals, every one of you watching this lecture. It's starting to look like something you've seen, at least on TV. Heartbeat. Is that what you guys said? No. Kane got it. Kane, you get triple snacks if you ever show up. Yeah, so that's the systolic heartbeat. So it's just showing you that it's not just toy signals like square waves and triangle waves. And this is done from data. So this is just data collected on a heartbeat. It's not a function, etc. And yeah, heartbeat. Okay, so the individual terms we were adding up. Well, I've got them in the handout, so we'll go to the handout. Fourier series for veterans of linear algebra. You'll see how linear algebra ties in. So this is a topic that can only be done if you know calculus, and it's done best if you know linear algebra, though you don't have to know linear algebra. Okay? So let's review a few things from finite dimensional vector spaces like we did in Rob 101. So if we have a basis for Rn, so there's n vectors here. To be a basis, they should be linearly independent. And then you're guaranteed, because the dimension of Rn is n, that every vector in Rn can be written as a linear combination of n linearly independent vectors, any of them. Now, do you remember what orthonormal means? Ortho means orthogonal, okay? That means the dot product is 0. And normal means their length is 1. So if you calculate the norm. So orthonormal means if I do V1 dot V2, I get 0, and the same with V1, with V7, et cetera. But if I do V1 with itself, that's the norm squared, it's 1. So 1 squared is 1. So the norm of each of these V's is 1. So because this is a basis, we can take any vector in Rn and write it as a linear combination. Now this is a linear combination because it's finite, not infinite. Those are no longer linear combinations. And the magic is when the basis is orthonormal, you don't have to solve a set of linear equations to determine the coefficients alpha. You simply take the dot product of x with one of the basis vectors. So here's Vj. So that's all I've done here. I'm writing x, and these brackets are the inner product. So we're going to use the term inner product instead of dot product because dot product is usually limited to Rn, and we're going to do this more generally for functions. Okay, so you just do the inner product, and you guys remember how it is in Rn. You just take the transpose of the vector times the other one will be a column vector. That gives you a number, and you do the vector multiplication. Okay, so you do that, and because the dot product is linear, the inner product is linear on either side, we bring out the coefficient, and if these guys are orthonormal, their individual inner products are either equal to 1 when k and j are equal or 0 otherwise. So that's orthonormal. So if I want to calculate and express x as a linear combination of a orthonormal basis vectors, there's the calculation of the coefficients. It's one inner product. X transpose times Vj, or I guess for you guys, X transpose Vj. And that's what it looks like. So here I just have R2 because that's all I can draw. They're orthogonal. So if you take their inner product of V1 and V2 is 0. And if you take an arbitrary vector x, I can write it as a linear combination of V1 and V2. And then I sum them up and I get the vector x. So this little pink vector here, alpha 2 V2, where alpha 2 comes from this inner product, plus this little bit larger vector, alpha 1 V1, where alpha 1 comes from this inner product. I add those together and I get x. So I just take this vector and I move it to the head and I add it and I do head-tail vector addition. So that's decomposing x in terms of orthogonal components. Okay, so any vector in Rn can be expressed as the sum of x inner product with an orthonormal basis vectors times the basis vectors. Does that ring a bell a little bit from Rob 101? It's been a while since you've gone through that, so I understand it could be a little bit faint, okay? Now here's a corollary that comes from this observation here, is that if I have a different set of vectors, and here I'm not imposing that it's orthonormal and I'm not imposing that m is equal to n, but I'm saying you can show that this set of vectors is linear, this set of vectors is a basis if and only if the only vector in Rn that is orthogonal to all of the basis vectors is the 0 vector. let's just kind of look at this picture here. If we have a vector that's orthogonal to the first vector, then it has to be parallel to the second one, because we're in R2 and there's only one other vector orthogonal to V1. Okay, so if a vector has dot product with V1 that's 0, then it has to be multiple of V2. And the only multiple of V2 that gives 0. So if it's also, so if the vector then is also orthogonal to V2, that means that vector dot with V2 is 0, then that means the coefficient alpha 2 has to be 0. So I do V2 dot alpha 2 V2, and I get 0. That's only if alpha 2 is 0. So we're going to use this observation that one way to see that you have enough orthonormal vectors to do this is that the only vector orthogonal to the basis is the 0 vector. All of the elements of the basis is the 0 vector. Okay, so now we're going to do something a little bit more general. We're going to define an inner product on functions using an integral. So we'll just take piecewise continuous functions so we know how to integrate those with Riemann. I'll assume it's on 0t, but if it's minus t over 2, t over 2, t is going to be the period of our periodic function in a little bit. I'm going to define an inner product of two functions by doing integral 0 to t of f of t, g of t, dt. Now, the first thing I want you to notice is that this is exactly the same as the standard inner product. How can I say this? Evaluate this integral by putting ti's in here, and you can have a delta ti if you want as a weight, okay? So you would do this integral as a Riemann sum. You would have f of ti and g of ti added up. That would be this integral would be the sum of f of ti and g of ti. Wow, so if you just took f of 1, f of t1, t2, tn, and g, and you did their dot product, you would have exactly then the Riemann sum here scaled by whatever delta t you were using. So this is just a natural extension of doing dot product of vectors in Rn. And since you have an inner product, you can define the length of a vector, the norm. So we use the square root of the inner product of a vector with itself to get its norm in Rn, or the norm squared is the dot product of the vector with itself, and you do the same thing here. So what I'd like to suggest as an exercise is that we apply Gram-Schmidt to make the vectors t and t squared defined on the interval 0, 1. Let's try to turn that into an orthonormal set of vectors. Okay. So I'll go to a blank page. I'll go to a blank page. And write things down. But do so that I'm just going to set things up again. The inner product of two functions, integral 0 to t, f of t, g of t, dt. And I'm giving us two functions. The first one is t, and we'll assume, so this is capital T, 1. That's a function. And then we'll have u2 of t is t squared okay. So what's the first step of Gram-Schmidt if you want to create orthonormal vectors? V1 is u1 divided by the norm of u1. So calculate the norm of u1. So we're taking t equals 1 here. Okay. We're just going to do a few calculations, and then we'll move on to the kicker. What I want you to believe is that you can apply Gram-Schmidt to functions. So the integral from 0 to 1 of t squared is equal to 1/8, 1/3, 1/3. Yep. Okay, so then so this is equal to t then divided by the norm, which is the square root of 1/3. So this is the square root of 3 times t. Okay, so that's the first step of Gram-Schmidt. So what do we do on the second step? We write it as u2 minus alpha times v1, and then we choose alpha such that the inner product of v2 with v1 is 0. We want those two vectors to be orthogonal. In our case, two functions to be orthogonal. Okay? So see if you can write down the integral and all I'm going to do is put them in here. So it's t squared minus alpha times v1, and v1 was square root of 3 over 2. Excuse me, not square root of 3 over 2, just square root of 3. T. And then we've got okay, do we have it? What we need to compute? Inner product is integral 0 to 1 of the first term times the second term. And then we're going to solve for alpha to make this inner product 0. got something similar to that. Okay, so we just multiply this term through. T squared, t cubed, and the square root of 3. And then the minus alpha, square root of 3, square root of 3, t squared. So what's the integral from 0 to 1 of t cubed? 1/4, yeah. And then the t squared we already did. So there's the value of alpha that makes the two functions orthogonal. So you end up with V2 is U2, which was t squared, minus alpha square root of 3 over 4 times t. And then the final step, which we'll skip because it's just more grungy. I'm going to normalize V2 to have norm 1. And so that means inner product of V2 with itself equals 1. And so this is excuse me, we need to compute that. So we do that integral, we get another number, and then we scale V2, and we got the final V2. Okay, so the whole point is, you can start out with a family of functions and just apply Gram-Schmidt like you would. Now, doing these integrals by hand, no fun, but if you just have quad GK and a for loop, you can just go through the monomials and create an orthogonal basis, orthonormal basis, okay? So, so the whole point is we know how to do orthonormal bases in Rn, and if you accept that this is a valid notion of an inner product, and it really does look just like the sum I equals 1 to n f of ti, and it's scaled by delta t is all. And this looks like the dot product of you take f and you stack up all of its values at t1, t2, tn, and et cetera with g, and you just take their standard dot product. The only difference is the scale factor. Okay, so we can, once we have a notion of an inner product on functions, we can calculate orthogonal functions, we can calculate norms, etc. Okay, so we're going to define L2. So it's just a set of square integrable functions. So you do their integral over 0 to 2, the function squared, it's finite. We're assuming piecewise continuous, so the integral is well defined. Okay. So that's our vector space. You can add any two functions in there, you get another function in there. We'll say a countably infinite set is a complete orthonormal basis for this vector space if the functions are orthonormal meaning I enter dot product or inner product of phi1 with phi2 is 0, and phi1 with itself, which is its norm squared, that has to equal 1. So this equals 1, j equals k, 0 otherwise. Okay, so it's a compact way of saying that a bunch of vectors are orthonormal. And then the other piece we're adding in the definition is that the only function that is orthogonal to all of the basis vectors is the 0 function. That's the completeness. So building these things, we could build a complete orthonormal basis starting from the monomials, and that's been done. And so here's some of the standard ones, and the one that we used in our Fourier series. You take a constant to get rid of the average value of the function, a constant, and then you take sines, and the key thing is that these are harmonics because we've got multiples of the fundamental frequency. And t is the period of the signal. That's called a fundamental frequency. And so we have all of the harmonics, we have all of the multiples of the fundamental frequency. We've got omega naught, 2 omega naught, 3 omega naught, 4 omega naught, etc. And we do that for sines and cosines. And there they are. There's the first 10 of them plotted. Or together, the first 20, and I didn't plot the constant. You can do this with complex exponentials as well. Okay. So here's what a general Fourier series is. You take any complete orthonormal basis, then you can write a function on 0t as this infinite sum, where this is the inner product of the function with the basis vector times the basis vector. It's exactly this formula on steroids. Okay, so we have an infinite number of basis vectors, we add them up. So these coefficients, so this, if you want to write it as k equals 1 to infinity of alpha k, and remember those were sines, cosines, and constants. These coefficients, they're called the Fourier coefficients. And what's amazing is you can take a function which seems to have an uncountably infinite numbers of pieces of information in it, but you've reduced it to a countable set of coefficients. 1, 2, 3, 4, 5. So they're indexed by the integers. And these Fourier series, so what you're doing is decomposing the function in terms of sines and cosines and their harmonics. So there's the standard trigonometric Fourier series. Anytime you have a sine and a cosine, you can combine those into either a sine plus a phase or a cosine plus a phase. So there's another form of the Fourier series that looks like this. And then it's often very convenient when you're doing circuit analysis, so is to use the complex exponentials. So in EECS 215, where you're putting, well, you're actually putting complex exponentials through your circuit and evaluating the impedance and adding everything up. This allows you to take an arbitrary periodic signal through the circuit, and as long as you know how to do the modal analysis. Okay, and so this last part here is just doing what we were doing earlier, where we take the monomials, and if you're using quad GK, you can develop the Legendre polynomials. There's a whole bunch of things, Chebyshev polynomials. They're all just orthonormal families of functions, Hermite, different weightings on the inner product, and you get all these other famous ways to build orthonormal bases, and then with respect to any of them, you can do its Fourier series. So there's one package in Julia that for doing analysis of functions, it takes the function and it computes its Fourier series, and then it recognizes that suppose we did it with cosines and sines. It uses something a little bit more numerically sophisticated than this, but if you know the integral of cosine over AB and sine, you now can integrate f just by adding up known integrals for sine and cosine. So you calculate the Fourier series, and then you can integrate it. The same with differentiation. And so your function, these are in the background, they're in the basis. You have integrals and derivatives of those computed, and then you just evaluate derivatives at points by putting in numbers here and then adding them up, and then et cetera. So it's another way to deal with numerical approximations of functions. Instead of using trapezoidal rule or Simpson's rule, which uses quadratics, fit a set of functions that you understand really well. And then as long as these things are differentiable, integrable, et cetera, you can evaluate integrals by just doing integrals of each side, and they're already known and tabulated, or you can calculate derivatives by just differentiating these and adding them up, and second derivatives, et cetera. So it's kind of cool. The last thing I just want to make a few comments on is optimization. So we didn't do a lot of work on computing closed form solutions to differential equations. We looked carefully at linear systems, but for nonlinear, there's very few equations where you can just calculate in closed form the answer of the differential equation. So you've got to sneak up on the solutions. We learned how to solve them for a given initial condition using the differential equations package in Julia. But the way we get a lot of our robots to move is we do the following. We set up an optimization problem. So tau here is, say, the motor torques. Motor torques. So you want to minimize, say, the integral squared of the motor torques, subject to the differential equation is satisfied, our initial condition is satisfied, and maybe we have a desired final condition. Or maybe we're after some sort of periodic behavior and we want the to start at x0 and come back to it, okay? So what we often do then is exactly what you guys were doing in project 2, which is to enter the differential equations as a family of inner product, a family of equality constraints. Let's see if I can get this one to work. Yep, kernel's disconnected. No kernel to restart, thank you. Kernel is connecting. So this might help your summer project, Devin. When we can run something as simple as just pulling a file into the workspace. I don't know why everything is so slow today. I'll reach out to Vocarium, let them know. Thank you. Okay. Okay, so this is kind of the simplest possible walker that you can have, and it's too bad it won't fit into it. So it's got a torso, It's got a torso and 2 legs. This one has no knees, so it can only shuffle, okay? But it's got 3 legs. It's simple, just point mass at the head of it, point mass at the hips, and 2 point masses where the knees would be, okay? So that's the robot. Here's the terms in the dynamic model. So it's the standard robot equations, D times Q double dot plus C of Q, Q dot times Q dot plus G equals, etc. Okay, so there's no way that you can solve those equations by hand, okay? So what we do is we set this up in jump. Okay, so we're going to set this up in jump where we have initial guesses, but they're not constrained to be there. We're going to constrain that we get a periodic walking motion. And a lot of this time is just loading all these various packages. It's not taking it takes, I don't know, 300 milliseconds to do the optimization, something like that. The dynamics are set up as equality constraints. using the trapezoidal rule. What do we got, a denial of service attack on Vocarium here? Oh, not exciting for any of us.
Oh, there we go.
There we go, yeah, so we got it. So now we'll look at the results. This is going to make a bunch of plots. Okay, so the step here is 400 milliseconds, so it's already done 10 steps, okay? So this is a very nice step, and then it hits and restarts again. So this is just one step. And then it's periodic, and it's minimized the amount of torque. So the motor torques are quite low. They're 10 Newton meters here and a peak of about 25 here. Given a standard gear ratio that was used on this generation of robots of 50-1, it means the motor, if it has 1 Newton meter, then we're only using half of the motor torque, okay? So that's a... Now what you can do is take this, and there's some references in here, Devin, where you guys can learn to design much better controllers than I have in here. And when you get stuck, you can come talk to me. Okay. So here, I've got a feedback controller on it, so it can do multiple steps now. Yes, I know the kernel's busy, and the kernel shouldn't be taking this long to run this. Yeah.
You can go to break if you want to do this thing, if you want.
Should we just pass out the snacks, is what you're saying? Yeah, I was going to wrap this up, and then we just have snacks and chat, but the only thing to observe here, there we go. So there we've got all of the bunch of steps. Now it's going to make the GIF, and it's vigorously, and then the controller is stable because you see I had it walking really fast, and then it's slowing down now to a periodic orbit. Okay, so you've got the feedback code in here. So you just go to chapter 10, there's 4 different things there, and then the code that generates the Lagrangian model of the biped is given. You need a little bit more than just this, but it's already a great start. And if your team gets to a point where you want more than this, happy to help you out. Okay, so that's kind of the end of the lecture. Any questions online for us? So you've got access to examples of using JUMP, which is a really nice optimizer in Julia, to set up differential equations and compute solutions to them that way. And that way you can impose conditions on the equations like this. It's making not overly taxing the motors. I've got conditions on the foot when it impacts the ground to be soft and things like that. So, okay. So,
You guys gotta help me out. I got you, okay?
So Monday, once again, we're going to work the practice final, and it'd be great if you could work it over the weekend or at least scan through it, and then we can talk about how you might work on your cheat sheets. You have some ideas. Okay, so